Forces, vectors and scalars. Every measurement in physics is either a scalar or a vector. A scalar has size only. Examples include speed, distance, mass, energy, and time. A vector has size and a specific direction. Examples include velocity, displacement, acceleration, force, and momentum. Velocity is just speed with a direction, like 60 miles per hour north. Displacement is just distance with a direction, like 5 meters left. Contact and non-contact forces. A force is a push or a pull. These are split into contact and non-contact forces. Contact forces need physical touching. Examples include friction, air resistance, tension in a rope, and the normal contact force which holds an object up, such as a book on a table. Non-contact forces act at a distance through a field without touching. Examples include gravity, electrostatic force, and magnetic force. Graphs are a massive trap in the exam because two lines can look identical but mean completely opposite things. You must check the label on the left axis first. So graph 1, the distance time graph. Think of this one as, how far away am I from home? A flat horizontal line means you're stationary. You've stopped moving, your distance from home is frozen. You might have stopped and had a chat with a friend, or gone into the sweet shop. A straight diagonal line going up means you're moving away at a steady, constant speed. The gradient or steepness of the line tells you exactly how fast you're going. Are you sprinting, walking, fast or slow? A steep line means sprinting. A shallow line means walking. If the line is curved, it means you're changing speed. You could be slowing down or you could be speeding up. If examiners ask you to find the speed on a curved line, you must draw a straight flat tangent to the curve at that exact second and calculate the gradient of that tangent line. The velocity time graph. Think of this graph as answering the question, what does my car speedometer say? A flat horizontal line does not mean you've stopped. It means you're moving at a constant velocity. Your speed is frozen at one steady number, like cruising down the motorway at 60 miles per hour. A straight diagonal line upward shows constant acceleration. You're stepping on the gas pedal and steadily speeding up. A diagonal line downward shows deceleration. You're stepping on the brakes and steadily slowing down. The gradient of any line on this graph gives you the acceleration. In the exam, if they ask you to find the total distance on a velocity time graph, don't look at the lines. Look at the empty space under the lines. Split that space into simple math shapes like triangles and rectangles and work out the area of each and add them together. That gives you the total distance every single time. For foundation tier, there's an equation you need for acceleration. Acceleration equals the change in velocity divided by the time taken. Here, u is the initial velocity, v is the final velocity, and t is the time taken. This equation tells you how quickly an object's velocity changes. If the object is speeding up, the acceleration is positive. If it's slowing down, the acceleration is negative, and this is called deceleration. Let's try an example. A car starts from rest and reaches a speed of 20 meters per second in 5 seconds. Find its acceleration. First, write down what you know. U equals 0 meters per second. V equals 20 meters per second. T equals 5 seconds, and A is what we're finding out. Now substitute the values into the equation. Acceleration equals 20 minus 0 divided by 5. 20 divided by 5 equals 4. So the acceleration is 4, and don't forget the units, meters per second squared. Let's try another one. Find the acceleration. A cyclist slows down from 12 meters per second to 4 meters per second in 2 seconds. Find the acceleration. Write down the values. U equals 12 meters per second. V equals 4 meters per second. T equals 2 seconds. Now substitute them into the equation. Acceleration equals 4 minus 12 divided by 2. That gives minus 8 divided by 2, which equals minus 4 meters per second squared. The negative sign tells us the cyclist is slowing down, so this is deceleration. In the exam, always start by writing down U, V, T, and A. Then identify the one you need to find before substituting the others into the equation. How do we explain these graph lines? Newton's laws explain motion. Newton's first law states an object will keep doing exactly what it's already doing unless an unbalanced leftover force acts on it. If an object is sitting still, it stays still. If an object is already moving, it keeps moving at the exact same constant speed in a straight line. The second law defines force as mass times acceleration. F equals ma. The third law states that for every action, there's an equal and opposite reaction. A typical exam question for Newton's first law is a skydiver jumping from a plane. It happens in 5 distinct stages based on forward, backward, balanced and unbalanced forces. Stage 1 is the jump. The moment the skydiver steps out of the plane, the downward pull of gravity, their weight, is the main force. There's zero upward air resistance yet. The forces are not balanced, there's a large downwards leftover force. Because the forces are unbalanced, the skydiver accelerates rapidly in the downward direction. Stage 2, speeding up. As the skydiver falls faster, they smash into air molecules. This causes the upward air resistance force to increase. The downward pull of gravity stays the same. The forces are still not balanced, but the upward force is now fighting the downward force. The resultant downward force gets smaller. The acceleration slows down. Stage 3, terminal velocity. Eventually, the upward air resistance force perfectly matches the downward pull of gravity. The forces are now completely balanced, and the resultant force is exactly zero. This is Newton's first law. Because the forces are balanced, there's zero change in speed. The skydiver stops accelerating entirely and drops at a steady, maximum constant speed. This is called terminal velocity, and it creates that flat horizontal line on a velocity time graph. What happens next are the parachute stages, and sometimes examiners do ask what happens when the parachute opens, and this adds 2 more stages to the story. So stage 4, the parachute opens. Opening the parachute drastically increases the surface area. This causes a massive sudden increase in upward air resistance. The forces are not balanced. The upward force is now much greater than the downward force. Because the big resultant force now points upwards, the skydiver slows down really quickly. A mistake that students do make is saying that the skydiver moves upward into the sky. They're still moving in the downward direction, but they're just decelerating rapidly. Stage 5 is that new safe speed. As the skydiver slows down, the wind doesn't hit them as hard, so the upward air resistance drops until it matches the downward gravity force for a second time. The forces are again completely balanced, and this is a new, lower terminal velocity. Because the forces are balanced, the skydiver stops slowing down. They cruise at a new, much lower safe constant speed all the way to the ground. The skydiver landing. When the skydiver finally hits the grass at the end of stage 5, their boots push downwards on the ground. At the exact same microsecond, the ground pushes upwards on the boots with an equal force. We can now move to Newton's second law. We use the equation force is mass times acceleration, F equals m times a. This formula tells us that acceleration depends on the size of the resultant force and the mass of the object. Required practical, force and acceleration. This practical tests how force or mass affects acceleration. A trolley is placed on a track and pulled by a string attached to weights over a pulley, and these hang off the edge of a table. The force is the pulling power from the weights hanging off the edge, and if you want a bigger force, you add more hanging weights. You can change the mass by adding extra metal masses on top of the trolley itself. The acceleration is how fast the car speeds up. We don't use humans with stopwatches because they're too slow. Instead, we use 2 light gates like high-tech speed cameras. One measures the car's speed at the start, and the other measures its speed at the end. The computer calculates exactly how fast the car accelerated between the 2 gates. And this is the whole setup. You're just changing the force or the mass, letting the trolley roll and letting the light gates measure the speed. In real life, imagine driving down the road, then a hazard appears. From the moment a hazard appears to the moment the car is finally still, it keeps travelling, and the total stopping distance is 2 parts added together. Stopping distance equals thinking distance plus braking distance. Thinking distance comes first, the gap between seeing the hazard and your foot reaching the brake. The forward force from the engine and the backward forces of air resistance and friction are balanced, exactly like Newton's first law and the flat line on a velocity time graph. Thinking distance is how far the car travels during your reaction time. Anything that slows your reactions makes it longer. So being tired, drinking alcohol, taking drugs, or looking at a phone all stretch the thinking distance out. Braking distance comes second, and it's the unbalanced forces phase. Now the brakes are on, the forward force is gone, and a big backward friction force takes over. So the forces are unbalanced and the car decelerates. To see how mass changes the force needed to stop a vehicle, imagine a heavy lorry and a small car driving side by side at 60 miles per hour. Mass is a measure of an object's inertia, which is its reluctance to change its motion. It's harder to start a heavy object moving, and it's harder to stop a heavy object once it is moving. To stop safely in the exact same distance, the heavy lorry and the small car need the exact same deceleration. Because the lorry has a much bigger mass, the formula F equals m times a proves it needs a much bigger backward braking force to slow down at the same rate as a small car. Let's say 5 meters per second squared. Deceleration. Look at the formula. Force equals mass times acceleration, F equals ma. For a small 1,000 kilogram car, you multiply 1,000 by 5. The car needs 5,000 newtons of braking force to stop. But a heavy lorry has a mass of 10,000 kilograms. You multiply 10,000 by 5. The lorry needs 50,000 newtons of force. Because the lorry is 10 times heavier, the mass proves it needs 10 times more braking force to slow down at the same rate. In the exam, if the lorry is overloaded with cargo, its mass increases, and that means it needs even more braking force to stop. If the road is wet or icy, the tyres lose their grip, meaning the brakes can't physically generate enough backward friction force. Because the force drops, the lorry can't slow down quickly and will slide much further, drastically increasing its braking distance. A moving car has lots of kinetic energy. And when that car comes to a stop, the energy doesn't just disappear. When the brakes are applied, friction does work and transfers the car's kinetic energy into thermal or heat energy. This is calculated using the formula work done equals force times distance, W equals F times D. Work done is just a physics word for the total amount of energy you need to transfer to bring the car to a stop. To put it simply, work done changes one form of energy into another form of energy. Let's say a moving car has 50,000 joules of kinetic energy. To stop the car, the brakes must do exactly 50,000 joules of work. If the driver slams on the brakes and creates a massive friction force of 5,000 newtons, we can find the distance. 50,000 divided by 5,000 means the car stops in 10 meters. But if the road is icy, the tires slip and the friction force drops to only 1,000 newtons. 50,000 divided by 1,000 means the car now takes 50 meters to stop. Because the force dropped, the braking distance multiplied just to transfer the exact same amount of energy. So the brakes get hot, and the faster you're going, the longer the braking distance. Finally, we have Newton's third law. And a lot of students get mixed up between the first and the third law. So imagine you're sitting on a skateboard. Newton's first law says that if you're just sitting still, you'll keep sitting still unless someone pushes you. And if you're rolling, you'll keep rolling unless someone stops you, like a bump or friction. Basically, things like to stay how they are unless something makes them change. Now, Newton's third law says if you push on something, it pushes back just as hard. So if you push off the ground on that skateboard, the ground pushes you forward. Every action has an equal and opposite reaction. So the first law is about staying still or moving unless something changes it. The third law is about every push having a push back. Gravity, mass, and weight. Mass is the amount of matter in an object. It stays the same anywhere in the universe and is measured in kilograms. Weight is a force of gravity pulling on that mass. Your weight changes depending on where you are in space. So your weight on Earth would be different than your weight on Saturn, but your mass on Earth would be the same as your mass on Saturn. Weight is a force, so it's measured in newtons. Mass and weight are linked by this formula. Weight equals mass times gravitational field strength, W equals m times g. On Earth, gravity is roughly 9.8 newtons per kilograms. Weight acts from a single point called the centre of mass. In the exam, if the question gives mass in grams, divide it by 1,000 to get kilograms before you calculate the weight. Required practical, stretching a spring. In this practical, you test how a spring stretches. Hang a spring from a clamp stand next to a vertical ruler. Measure the original length of the spring at eye level. To avoid reading errors, use a horizontal pointer attached to the bottom of the spring. Add weights one by one. Each time you add a weight, record the new length. Calculate the extension by subtracting the original length from the new length. Extension is the change in length, not the total length. A graph of force against extension shows a straight line through the origin. This proves that extension is directly proportional to the force applied. The formula is force equals spring constant times extension. F equals K times E. The spring constant measures how stiff the spring is. A steeper line means a stiffer spring. If you add too much weight, the graph bends. This point is the limit of proportionality. Past this point, the spring is permanently damaged and will not snap back to its original shape.